Okay, well, welcome back, everyone. We either got a test coming up here soon, or maybe you're just experiencing some insomnia and you want to hear some chemistry problems to put you to sleep. But we're coming up on the third exam here in Chem 151. So there is a practice exam you'll find posted on the course Moodle page, and I'm just going to try to go through and solve some of these problems for you. Hopefully match the answers you've already gotten as you practice these problems, but maybe straighten out some misconceptions you might have had along the way. So just jumping right in, looking at the first problem here, we've got some light, right, or radiation used to break a chemical bond. And we need at least 941 kilojoules per mole in terms of the energy required for this process to break this nitrogen-nitrogen bond. We want to figure out what is the longest wavelength of radiation that possesses the necessary energy. So as the wavelength gets shorter, that would mean higher energy. So basically we want to find the wavelength that can be associated with this energy. Now, one of the tricky things here is this energy is basically in enthalpy units, kilojoules per mole. So this is describing the enthalpy of this chemical process. But the way we can relate wavelength to energy of light only applies to a photon. So the first thing we need to do here is take our energy and convert it to figure out how much energy each photon would contain. And in the process, we want to change kilojoules to joules as well, because then it'll fit with some of the constants we'll use in our equation to solve for wavelength. So if I cancel out kilojoules and convert that to joules, that would require multiplying by 1,000, because there's 1,000 joules in a kilojoule. Right? If I stop there, I'd have joules per mole. Joules is what I want, but I don't want moles. So if I put 1 mole on top here, 1 mole of photons would be 6.022 times 10 to the 23rd photons. And we need to get our units into describing the energy of an individual photon for that equation we have to apply. So that would cancel out moles. Now I have joules per photon. That is exactly what I want. So punch this into my calculator. 941 times 1,000 divided by 6.022 times 10 to the 23rd. And this is 1.5626 times 10 to the minus 18th joules per photon. Okay, so that is not the answer to the problem, but we're headed in the right direction. Once we have the energy for the photon, we can think about how we can relate this energy to the wavelength of the light. So we probably first talked about the formula this way: the energy of a photon, Planck's constant times the speed of light, divided by the wavelength. If I rearrange that equation, I can get wavelength on one side. That would be Planck's constant times the speed of light divided by the energy per photon. Right? Planck's constant and the speed of light are constants, so we can plug both of those in. And to be clear, on a test I'll give you the constants. You do need to know how to use them, right? How your units are going to work out, etc. But you don't have to memorize what the constants are. And then divide by our previous answer there, joules. Now, this photon part, right, this equation only works for photons, but don't get too caught up in how does the photon unit play in with the units down here. It doesn't. We just need to figure out how many joules are associated with each photon before we can use this equation. So don't try to throw photons as a unit in here. Everything is going to cancel out except meters. That will give us this wavelength in meters. Punch in all your scientific notation correctly here, right? And now we can worry about sig figs. We started with 3, so 1.27 times 10 to the minus 7th meters would be the wavelength here. Now, this type of light, it's probably more reasonable to change this to nanometers. So that wasn't asked for in the question, but let me put that in as a possible step here. Multiply by 10 to the 9th. This would be 127 nanometers for the wavelength of this light. Okay, seems very likely that you'll see a problem like that on the exam. And the other thing to think about here, if I want to just mix this problem up a little bit, instead of giving you the energy, I could give you the wavelength. If I give you the wavelength of the light, you're really doing the same calculation, just in the reverse order. You could plug wavelength in here, right, as long as you convert it to meters, so it cancels with your speed of light meters. Calculate the energy per photon, and then work your way back to what would be the enthalpy value for that reaction in terms of kilojoules per mole. Okay? So same math, just going in the opposite direction. Okay, question number 2. We want the values of N, L, and M sub L for, and then we're given some different subshells. The important thing to keep in mind here, N is the energy level. That's the first quantum number. And L is the sublevel. That's the second quantum number. So once we're given this nomenclature, 2p, that's both the energy level and the sublevel. So M sub L is the only one that will have multiple values here, since we've already indicated one specific value for N and L for each of these. M sub L, remember, indicates the number of orbitals in each sublevel, so it'll be dependent on what the value of L is here. So for A here, N, the energy level for the 2p subshell, is 2. Right? Please don't miss that one on the test. N is this number that comes out in the front. That's whatever energy level we're talking about. If there's a problem on the test where I say, what is the energy level of the 2s orbital? Please say 2. That one is very disappointing to have to mark wrong on the test, since it's right there. Now, the sublevel or subshell here is a little more complicated because we use the letter designation. But remember, there's a 0 value for L, so the S sublevel is L equals 0. That means the P sublevel is L equals 1. Now, when L equals 1, that means there are 3 values for M sub L, -1, 0, and 1, right? Which is how we know there are 3 orbitals in a P sublevel. For part B here, the 5D subshell, that is the 5th energy level, so N equals 5. For a D sublevel, L is equal to 2. Remember, the order is S, P, D, F, G, H, I, right? After F, it's alphabetical order. So D would correspond to L equal 2. Now, if L is equal to 2, that means M sub L will span from -2 up to +2. So there will be 5 possible values for M sub L. And the way that kind of relates to electron configuration is that there are 5 orbitals in every D subshell or sublevel. For C, 6H, so that again would be the 6th energy level, so N is equal to 6. Now for H, let me put these over here, S, P, D, F, G, H, 0, 1, 2, 3, 4, 5. H would be L equals 5, right? We don't see that on the periodic table, but those fairly straightforward quantum number rules tell us it's there within the structure of atoms. Now, if L equals 5, that means there should be 11 values here for M sub L. They would go from -5, say -5 while you're trying to write -3, all the way up to 0, and then continue on up to +5, just the integer values. So 11 orbitals would exist if we got to a place where we had an H sublevel. Okay? So quantum number rules, should be pretty familiar with the quantum number rules and kind of how they apply there to electron configurations. Similar idea here for number 3, which of the following represent impossible combinations? So this goes back to the rules establishing N and L. So remember, L is equal to 0 up to N minus 1. So when N equals 1, the only possible value for L is 0. So this one is not possible. There is a possible 1s sublevel, but not a 1p, because that would imply N equals 1 and L equals 1, and L can't equal 1 when N equals 1. Now 4s, that is possible. That would be N is equal to 4, L is equal to 0, so that is fine. 5f is also possible, because if N equals 5, L can equal all the way up to 4, and for an F that is L equals 4. So that would be the highest energy sublevel within the 5th energy level. Now 2D, that's not possible, because if you start with n equal 2, the only values you can have for L are 0 and 1, which is the S and the P. So there's a 2S sublevel, there's a 2P sublevel, but there is not a 2D sublevel. And then part E here, 11M. So if we go all the way up to the 11th energy level, is there an M sublevel? So if N is equal to 11, that would mean L can have values of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? All the way up to n minus 1. And that would be S, P, D, F, G, H, I, J, K, L, M. So that indeed is possible. There would be an 11M sublevel in the 11th energy level. Okay, we'll stop right there. We'll come back for the next page in the second video.